Okay, so this is the 4.1 lecture for pre-calc. I'll do it in two parts. So I'll do page 1 and 2, stop the video, and then I'll record 3 and 4 in the second part. So a few definitions at the beginning here. You can see they're talking about the initial side and terminal side. So with the initial side and terminal side, we start here as the initial side, and the terminal is talking about where do you end up. So that should make sense. Initial, start, terminal, end. And those two things, the vertex is where the two rays meet, and how far does that angle open up. So example, if the initial side of an angle is at 32 degrees and the terminal side is at 100, what is the measure? You can just subtract the 100 minus 68 is equal, minus 32 is equal to 68 degrees. So that shouldn't be too bad. But typically what we do is we put something in what's called standard position. So we're going to always start here at the positive x-axis. So we'll always have one side sitting here, and then we'll open it up to another terminal side. So we're all doing the same thing. So for example, if we do 120 degrees, I would go to positive x, start there, open up 90 degrees, and then 30 degrees more, so it would be about right here. So this would be 90, an additional 30. So it would look like something like that, and we would end up in quadrant 2. Now, typically our quadrants are in Roman numerals, but quadrant 2 would be okay. So then, one of the things we talk about are positive angles and negative angles. Positive angles will be counterclockwise. So you'll start at the positive x-axis and go upward first. Whereas negative angles will start at the positive x-axis and they'll go clockwise, just like the hands of the clock. So they'll move down from the positive x-axis. So if I was to draw something that was negative 320 degrees, I would draw in my xy axis, and then basically you can count, if you want, by 90s. You can go 90 degrees in the negative direction, another 90 in the negative, and another 90 in the negative. So these are all 90 degrees, and I'm at 270, plus an additional 50, if you will, in the negative direction. So 90, 90, 90, and 50 is 320. But we're in the negative direction, and so we end up right about there. And again, this would be quadrant 1 or Roman numeral 1. So that's just kind of getting started, why we use the x-axis, positive x-axis, and we measure things. As we do more, it certainly will become easier for you to understand or be comfortable with. We also talk about radians, and if I really set up the class to talk about radians, I would give everybody a pie plate, and I would ask you to measure the radius. So when you measure the radius, then I would ask everybody to come up and get a piece of string, and we'd cut that string to the length of your radius, and then we would put that along the axis, so we would, around the circumference, so we do one there, and then a string there, and a string there, and a string there, and another string there, and another string there, and then something like this. And what we'd find as you go all the way around and you keep putting the strings down is everybody would get about 6.28 pieces of string around, or 6.28 radius. And so you notice there's a relationship. Well, 6.28 is approximately 2 pi. So this is where the relationship happens. Take a circle, how many radii can you fit around your circle? The radian measure of any central angle is the length of the intercepted arc divided by the circle's radius. So this formula, kind of tough to see, theta equals S over R, where S is the arc length, and R is obviously the radius, and then theta is the central angle, but it has to be in radians at all times, that angle. Whenever you do these problems, we're going to be in radian mode. Otherwise, you have to do a conversion, which you might remember from your geometry days, doing a conversion. We can talk about that later. So the arc length is always this measurement out here on the circle. So for instance, a central angle, theta, in a circle of 6, or a circle with a radius of 6 inches, intercepts an arc length of 15 inches. So if we were to draw this picture, I would draw a circle, I would draw in a radius of 6, an intercepted length, just kind of estimate it, something like this, would be about 15 inches. And then what's happening is we're creating an angle, this central angle, and they're asking us for that angle. So then we can just do theta is the intercepted arc, 15 divided by 6, and if you simplify it, that'd be about 2.5. A lot of kids want to put pi on there, so they write pi, and then it's wrong because 2.5 pi is like 2.5 times 3.17. Well, that's not the number we have. So always remember that theta is already in radians. So remember 2.5 radians, go back to the problem we talked about, it would be taking your piece of string and laying out 2.5 pieces of string. That's the intercepted arc. That's what they're talking about, the central angle would be. Arc length, you can use the same formula for the fact that the arc is a fraction of the circumference. So now that's the formula right here that some of you might remember from back in the day with geometry, because they're converting using x over 360 to put it into something a little bit more manageable, I guess. A circle has radius of 12 inches. Find the length of an arc intercepted by a central angle of 110 degrees. Use exact answers only. So again, if you're drawing your picture, has a radius of 12 inches. Find the length of an arc, so they're talking about something out here when this thing is 110 degrees. Well, you can't use 110 degrees for this particular formula. You always have to be in radians, and so that's what this does. It converts to radians. So the arc length, which is s, if you multiply both sides of this function by r, would be r times your theta. So the r is 12 inches times the angle, which is 110 degrees, but then we're multiplying by our factor, 2 pi over 360. And so we'll talk more about these conversions, but that's what, if you bring this formula down here, that's what we're doing. I have my radius, I have my 2 pi, and they have it where the 360 is over here instead of here. Same thing. But anyway, all you have to do now is simplify that out, and you get 22 pi over 3. So basically, you can go to your calculator, you can take your 110 divided by 360 times 2 times 12. Now notice I didn't put pi in there, because if I put pi in there, it's going to give me a decimal approximation. And so I get that, and I can hit math, enter, brings me back to 22 thirds, and so I write 22 thirds down and the pi. Another example, the area of this circle is 64 pi. The area of a shaded sector is 16 pi. So remember, the figure is not always necessarily drawn to scale. What is the length of the arc ABC? So we're trying to find the arc length out here. So to accomplish this, we would still use our same formula. with the area now. So remember, the area of a circle is pi r squared. So with a formula being pi r squared, we're looking at pi r squared equals 64 pi, divide by pi, divide by pi, r squared is 64. Now r could be plus or minus 8, but r is going to be 8. So I know the radius of this thing is 8. It does make sense to have a radius that's negative. So now what I can do is go back, and I know since the area of the sector is 16 pi, you could have done this earlier, and the area of the circle is 64 pi, the pi's cancel out, and 16 divided by 64 means 1/4. So that's why they say it's not necessarily drawn to scale. The sector they've actually done is 1/4 of the circle, so it probably should be looking more like this, you know? So you can see that it's one quadrant. It's 1/4 of a circle. So at the end of all this, I can go back to my formula, which we just did. The S equals R times theta. And when you look at this, I don't have anything about the angle right now, or we could do 1/4 of a circle. So if a circle is 360 degrees, all the way around a circle is 360 degrees, or all the way around a circle is 2 pi radians, I simply can take S equals R, which is 8, times 2 pi, but I don't want the whole thing, I only want 1/4 of it. And so if you multiply this out, 1/4 of 2 is 2, and 2 times 2 is 4, so I'm ending up with 4 pi for the length of the radius. You could also go to a circumference type formula. Circumference, remember, is 2 pi r, and so I would do 2 pi times 8, but again I only want 1/4 of that. And so you'd also end up with 4 pi there. So a little bit different, you gotta think about it. Talk about circles, arc lengths. Find the central angle of a circle with radius 5, which intercepts an arc length of 2.356. So theta equals S over R is always the formula that I have memorized. So the central angle of theta, so now I can just plug in 2.356 divided by 5, and when you do this, you get 0.4712 radians. So if you wanted to leave it there, that's fine. That's 0.4712 radians. You could go ahead and convert to degrees, but we don't have to at this time. Coterminal angles. Coterminal, they share a terminal side. So basically all you do is spin around 2 pi or 360 degrees. So for example, if I drew a 30-degree angle, somebody could start at 0 and they could wrap around and go to that spot, and now that would be 360 plus 30 or 390. But they share that same terminal side. So two angles are coterminal if they share the same initial side. You can find an angle that is coterminal with a given angle if you either add 2 pi, spin around 1 revolution. We're looking for counterclockwise here. Counterclockwise. Or subtract 2 pi if you go in the clockwise direction. Just talking about positive or negative angles. So to find a coterminal with 7 pi over 4, one of the suggestions is I would just stay in radian mode. So I can take 7 pi over 4 and add 2 pi. or I can take my 7 pi over 4 and subtract 2 pi. Now the easiest way is to use a calculator. You could get a common denominator, that's fine. But if you take 7 divided by 4 and you add 2, then hit math, enter, enter, it brings you right back to 15 over 4. So 15 over 4 pi. Do it the other way, 7 divided by 4 minus 2. Math, enter, enter. So I take pi out and I put it back in. So I have negative 1 over 4 pi, which is probably better to write just negative pi over 4. So finding coterminals in radians, even though it's a fraction, I would just use the calculator. So there's unlimited numbers of answers that you can do. So again, go ahead and pause the video now, do a couple of these, add 2 pi and subtract 2 pi to both of these and see what you come up with. Alright, so hopefully you pause the video, and what you're going to do is take your 5 pi over 6 and add 2 pi. You're going to take your 5 pi over 6 and subtract 2 pi. When you add your 2 pi, you're going to end up with 17 pi over 6. And when you subtract your 2 pi, you'll end up with negative 7 pi over 6. All the easiest is just go into the calculator. You can certainly get common denominators for these and do it that way. So again, they want one positive, one negative. So pi over 6 plus 2 pi and pi over 6 minus 2 pi. So these are pretty easy to do because you could cross off the 2 and make that 12 pi over 6. It's the same thing. Then you get 13 pi over 6. And over here, if you subtract it again, you would have 12 pi over 6. But subtracting, you end up with negative 11 pi over 6. So I'm going to stop the video now, and I'll finish part 2 in a second.